Hello everyone, welcome to another video lecture. To kind of get your brain ready to go for the new stuff we're going to talk about today, I just have kind of a thinking little activity I'd like to do with you. Go ahead and do this on your output page in your notes. So I've got a diagram of a Bohr model here. So you see the red dot in the middle is your nucleus, and then it's got energy levels 1 through 7 shown. This is a pretty accurate model of what the energy levels would look like if you could just sort of like cross-section them like this. So energy level 1 being that first one, and then going up to 7. Remember, N represents energy level. So looking at that picture, I've got a couple questions I'd like you to think about and then answer on your output page in your notebook. First question, what is happening to the energy levels as they get farther from the nucleus? Go ahead and take a look at that. So here's energy level 1, here's the nucleus. What do you notice about the energy levels as you get farther away? This is pretty much a level 1 question because literally just what do you notice? And then the second question, this is a level 3 question. So if this is the way they look right now, what would you predict will happen to the energy levels as we get into row 12 on the periodic table as we discover or create new elements? Right now there's only 7 rows on the periodic table matching the 7 energy levels for the elements we have. So what do you predict will happen if we got up to row 12 on the periodic table? Go ahead and pause the video and think about those 2 questions, answer them, and then we'll talk about it. All right, welcome back. Okay, so first question, what's happening to the energy levels as you get farther from the nucleus? What I'm hoping you notice is that they get closer and closer and closer together. The idea here is that if you're at level 7 and you're an electron with a negative charge, you still have to be attracted to that nucleus. So as you get farther away, the energy levels get closer together so that they still can feel the attraction of the protons in the nucleus. So then with that idea, what do you predict will happen if we got all the way to row 12? Well, the idea is that these rings would keep getting bigger around, but they would have to be getting closer and closer and closer together because, again, otherwise those electrons that are way out here aren't going to be able to be attracted to that nucleus, and it'd be super easy to take those electrons away, which could be really important for bonding and other things that might happen. So just a little bit to think about as we go into our new topic for these video notes. All right, here we go. If you didn't do electron configuration part 1 video notes, you should go back and do those. Otherwise, there will be a lot of things in these notes that don't make sense. So go back and complete those if you've not done so. But assuming that you have, let's move forward. The objective today is to use all of that stuff that we talked about in the quantum mechanical model and now put it into what looks like something usable. So instead of just a bunch of vocab words where we built the electron cloud, now we're going to talk about, well, what do chemists do with that information? Go ahead and turn that into your EQ. So you've got your guide at the end of the notes and the beginning of the notes of what should you be able to answer by the time we're done. Go ahead and get that set up. Let's get into it. So you're going to learn today something called an electron configuration. The purpose of an electron configuration is to describe how the electrons are arranged around the nucleus. So instead of just saying, oh, the electrons are in the electron cloud, that's not very specific. That would be like saying, oh, I live on Earth. Well, if you're trying to locate electrons, that's not very specific. So think about an electron configuration as an address. So if someone was going to mail you something, they would need to know your things like your zip code, your street, your house number, and then maybe even like your apartment, depending on where you specifically live. But think of it as like an address. So instead of just saying, oh, I live in Roseville, you also know what street you live on in Roseville, in which house number on that street, that kind of thing. Or you could think of it as like, what state do you live in? What city do you live in? What street do you live on in that city? What house number or apartment number do you live on in that street? So it's that specific. So instead of just saying electron cloud, we're going to be able to say what energy level, what sublevel, what orbital are those electrons in. So just getting really specific. Basically, to learn electron configurations, there's 3 rules you need to know. You need to know something called the Aufbau principle. Aufbau is a German word meaning building up. And it really just says that you have to enter the lowest energies before you can go to higher energies. So if you think about this kind of cross-section of an electron cloud, so imagine that the nucleus was here. Here's energy level 1. The Aufbau principle just says, hey, natural world is lazy. There is no reason for you to fill a high level if you don't have to. So the first thing you're going to try to fill up is energy level 1. If that's filled, then you go on to 2. If that's filled, then you go on to 3, then 4, then 5. So electrons enter and fill the lowest energies before they will go to a higher energy. So natural world is lazy. It's going to use the least amount of energy it needs to. And then that way you get that really good attraction between the electrons and the protons in the nucleus too. So it'll be more secure, which is another reason why it does that. The second rule is something called the Pauli exclusion principle. So to kind of understand this, first we have to just sort of review what's going on in the electron cloud. So we know that the electrons are going around the nucleus in kind of different patterns, but the electrons are also spinning on their own axis. So they spin on their own axis while they go around the nucleus, just like the Earth does around the sun, right? The Earth rotates on its own axis, which gives us our days, and it goes around the sun, which gives us our years. So that's the same thing that's happening inside an electron cloud. So the electrons are spinning in some direction as they go around the nucleus. So the Pauli exclusion principle is focused on that detail and says that if you have two electrons in an orbital, they will have to be spinning in opposite directions. So if one is spinning this direction and they're sharing an orbital, the other one would have to be spinning this direction. Because otherwise, if they're both spinning the same, that negative spin is gonna direct themselves out of the orbit of the atom, and then it just is lost. So we show it by this. So here's like a 1s, so energy level 1, sublevel S. There's the same orbital because there's only one orbital in the S's, just like there's 3 in the P. So this is showing by an up and down arrow. So it's saying, oh, this isn't possible. These two would be spinning the same direction. So instead, we're going to show that by an up and a down arrow. So if they're sharing an orbital, they have to be in opposite spins. That's the Pauli exclusion principle. And then the last one also has to do with orbitals. It's called Hund's rule. Hund's rule says that, okay, you've got a bunch of orbitals in some type of energy level. Like, for example, in the P sublevel, we know there's 3 orbitals. So if you're in 2P, you've got a 2P1, a 2P2, and a 2P3, right? That's kind of the idea. So what happens is the electrons are going to spread out as much as they can. If they can take their own orbital, they're going to. So visually, this is what it would look like. So let's imagine we had a 3D. The D sublevel has 5 orbitals, reviewing that from the quantum mechanical model we talked about in part 1. So if there's 5 electrons and there's 5 orbitals, they can each take their own orbital. They're only going to share if they have to. So for example, if I had 6 electrons, that 6th one would have to go and share, but remember it'd have to be opposite spins. So I would maybe do like an opposite upside down arrow. These are just one-sided arrows. That's often how they're shown just because it's faster to draw. So if you have 5 electrons in the 3D sublevel, they can each take their own spot. If you had 6 or 8, they would have to double up, but only if they have to. So the idea here is that we know that 2 electrons could have fit in this orbital. So if we had done that, that obeys Pauli exclusion principle. But the point is that they don't want to double up if they don't have to. So this is also 5 electrons in a 3D sublevel. But the point is that Hund's rule says this is not going to happen. Instead, they're going to each take their own orbital. It spreads out the negative energy as much as possible. They don't have to worry about spinning direction, and so they take their own seat if they can. So Aufbau principle, Pauli exclusion principle, Hund's rule. Those are the guiding things we think about when we're trying to write electron configurations. Okay, so that's kind of your level 1 information. So go ahead and do a level 1 Costa question. So it could be state Hund's rule would be a great level 1. So something just kind of straightforward from the notes. Go ahead and pause the video or come back to this later. All right, here we go. So how do we do this? How do we write an electron configuration? Well, we use the order of an energy diagram to help us remember the Aufbau principle, where you can only fill the lower ones first. If you look at this, you can see, so each circle is representing an orbital, and the S has 1 orbital, P's have 3 orbitals, and then you can see they're color-coded by energy. But up here, it starts to get kind of complicated. So instead, we have a way where we can sort of establish this pattern without having to memorize it. So I'm going to have you draw an Aufbau diagram. So draw kind of a big rectangle. Ideally, it would cover 7 lines in your notebook. And this is how you draw the Aufbau diagram. So you don't have to memorize the order that the electrons fill. Instead, we can just make this pattern. So start by putting 1 up until 7, starting with 1 at the bottom, up to 7. So there's your 7 different energy levels. So this will give us a chance to review part 1 notes as well. So this is your principal quantum number, your first one, 1 through 7. These are your energy levels. But then remember, the energy levels are divided into sublevels. and the number of sublevels matches the energy level up until 4, because 4 is the max, meaning that energy level 1 has 1 sublevel and it's an S, because that's the simplest. Energy level 2 has 2 sublevels, S and then also P. Energy level 3 has 3 sublevels, an S, a P, and a D, and they're going in order of complexity. So we're creating our pattern here. So 1 has 1S, 2 is 2S and 2P, 3 has 3S, 3P, 3D, and then 4 has all 4 of the sublevels, S, P, D, and what's the last one? F, you got it. So there's a 4S, a 4P, a 4D, and a 4F. But then there are no more that we have discovered at this point than 4 sublevels. So 5, 6, and 7 all have the same. Okay, get all of that written out. But then here's the tricky part. 1S fills, and that's obvious because there's no other choices. 2S fills, and then 2P fills, that's obvious. But once you start getting into more complicated areas of the electron cloud, parts of the energy levels and sublevels start to overlap. So to fill, it's not just as simple as all of the 1s, all the 2s, all the 3s, all the 4s. Because, for example, a 4D is really, really complicated. A 5S is not very complicated. So it turns out that sometimes some of these S's fill before some of the more complicated sublevels of a lower energy level. Here's what I mean by that. It actually goes by a diagonal. So start by drawing your first diagonal through 1S because 1S fills first. Then 2S fills because that's the next simplest option for electrons. Then 2P fills. And then 3S. So notice we're going in like a diagonal pattern. That's why it's important that you wrote these in like even rows and columns. After that, after 3S comes 3P. So far, this is what we would have predicted. 3S, then 3P. Here's where it starts to change. A 4S is simpler than a 3D. Now, to clarify, the 4 is a higher energy level, but the 4S is not as complicated as a 3D. So the 3D takes more energy to fill. So to clarify, 4 is higher than 3, true. But it's easier to fill a 4S, which only has 1 orbital and 2 electrons, than a 3D, which has 5 orbitals, 10 electrons. So when the natural world is trying to fill an electron cloud, it's going to do what's simplest first. And in this case, 4S is simpler. And then we're going to go back to the 3D. Then it goes to 4P, then it goes to 5S, and then that diagonal pattern continues. After 5S, go back to the bottom of your diagonal. Now it's 4D, then 5P, then 6S. Diagonal again, 4F, 5D, 6P, 7S, and then the diagonal continues. Now, technically, we don't have any elements that have this number of electrons, but the point is that it would just continue as far as we know. Now, maybe eventually we'll have an 8th level or a 9th level or something else, but this is the pattern that we have. So it really is just a pattern. I don't say that meaning, oh, this is super simple. It's pretty complicated, but the good news is you don't have to memorize the order. What you have to know is that there's 7 levels. The first level just has an S. The second has an S, a P. 3 has SPD. 4 through 7 have SPD and F, and it fills diagonally, always going back to the bottom of the diagonal arrow. That's the idea. So then now I just want to show some examples of, well, what do we do with this Aufbau diagram? And again, just kind of keeping this back in your mind, the reason we care about this is if we know the address of the electrons, we can predict what is it going to do in terms of energy given off, bonding, solubility even. There's lots, the shape of the molecule, all of that matters based on where the electrons are located. So that's why chemists care about this detail. Okay, so how do we do this? Let's do some examples. So the first example we're going to do is silicon. So if we're going to show the electron configuration, the first thing we have to know is, well, how many electrons are there? So we've got silicon, here it is. Silicon is element number 14. Then 14 is the number of protons, but because this is neutral silicon, it will also have 14 electrons. So that's the first thing we have to know. The next thing that we need to have is our Aufbau diagram that we just wrote. So you've got this in your notes, or here it is up on the screen again. So silicon has 14 electrons. Aufbau rule says we start by filling the first thing it can fill, and then it goes on after that. So the first thing it's going to fill is 1s. Remember that s's have one orbital, which is 2 electrons. So this is how we're going to write an electron configuration. It's going to be a list of where are the electrons. Energy level 1, sublevel s, 2 electrons. So 1s2. Then we go to the next part, the next thing to fill. Bottom of our arrow says that 2s comes next. S's have one orbital, that's 2 electrons, so 2s2. After 2s, we go to the bottom of our arrow, it fills 2p. Okay, now remember, p's have 3 orbitals, which can hold 6 electrons total. So now we're at 2p6. These are the number of electrons that are in that sublevel of this energy level. And remember, the total number of electrons is 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're at 10 electrons, and we have to get up to 14. So after 2p comes 3s. S's, we go back to only 1 orbital, so that's only 2 electrons. So then now we're at 3s2. So that's 12 electrons. So then after 3s, we go back to the bottom of the arrow in our pattern, and it's going to be 3p. The p does have 3 orbitals, but remember, we only have 14 electrons total, and we already have 1, 2, 3, 4, 10, 11, 12, which means that the last piece of our electron configuration will be 3p2. This is what an electron configuration looks like. It shows the different energy levels that are occupied. It shows the sublevels that are occupied. So then we would know the shape of the electron cloud. We'd have some circles. We'd have a couple dumbbells. This dumbbell would be bigger than this dumbbell. This circle would be bigger than this circle. And then these are the number of electrons located in that sublevel. And then the total number of these numbers at the top should equal the total number of electrons. This will tell us some things about, wait, that P sublevel is not filled. That means that silicon isn't stable. Like, these are the kinds of things that are useful when you look at an electron configuration. 14 electrons, think back to the flame test lab. That would tell us some ideas of how much energy could be produced by this element because of the number of electrons, the number of different levels that are available for jumping around. This is why this might be useful. Very specific to chemists, I get that. But I want you to think like chemists, which is what we're doing right now. Let's try one more just to get us a little bit more practice in this pattern. Let's do cesium. All right, so find cesium. Here it is. Element number 55, 55 protons, which, yep, that means 55 electrons. Okay, this gives us a chance to go through this pattern again. Aufbau principle always says you fill the lowest energy filled first, which is always going to be that 1s. S's have one orbital, so we're at that 1s2 again. We're going all the way to 55. So we know that for a while, all of these sublevels are going to fill. So then after 1s is 2s. So that's going to fill 2s2. After 2s comes 2p. That's going to fill. So that's 2p6. 3s after 2p. That's going to fill because, again, we have to go all the way to 55. And I'm only at 12 electrons right now. After 3s, we go to the bottom of our pattern arrow, comes 3p. The p has 3 orbitals, so that's 6 electrons because it's going to fill. After 3p, we follow our pattern, comes up to 4s. S's will fill because it's only 1 orbital, so 2 electrons. And remember, we have to go all the way to 55. So I'm at 4s2 right now. After 4s2, I go back to the bottom of my arrow, and now I'm going to fill that complicated 3d. D sublevel has 5 orbitals, which means it can have 10 electrons when it's filled. And it does fill because let's take stock. So 2, 2, and 6 is 10. This is 18, 19, 20, 30. We're only at 30 electrons. We got to get up to 55. Okay, so after 3D, let's follow the pattern. We go to 4P. P has 3 orbitals. That's 6 electrons. So now we're at whatever. Now we have 6 more of them. So that's what were we at? I can't remember. 10, 18, 19, 20. So now we're at 36. So we keep going, all right, because we have to get all the way to 55. So after 4p is 5s. S's only have 1 orbital, so that's 2 electrons, 5s2. Then now after 5s2, we go back to the bottom of our arrow, and now we're going to go to that 4d. 4d10 will fill because, again, we're trying to get all the way to 55. After 4d10, it looks like we can go up to 5p because this is between D10 and P6, there's not a huge difference in the number of electrons. So the 5 energy level is more important in that case. So that's why 4D fills before 5P compared to the S D2 compared to D10, that's a huge difference in electrons. So even though this is a 5, the S2 means it's not as much energy to fill as the D10 is. Okay, so 5p6. After 5p6 comes 6s. Oh, we got to take stock. How many electrons are we at? So 2, 2, and 6 is 10, 18, 19, 20, 30, 36, 37, 38, 48, 54. This means we're almost done. So after 5p comes, our next one is 6s, but we only had 1 electrons left, so it ends in 6s1. So again, now this tells us lots about what's going on in that electron cloud. What would the shapes look like? How big would the different layers be? How many electrons are in each of those sublevels? And then that can tell us about, well, what would this be likely to bond with? Is this more likely to fill this level or lose this level, to become stable, to bond, to give off energy? All of those kinds of things we can tell by looking at this address of the electrons called an electron configuration. All right, so with all of that kind of practice, the last thing that I want to do related to this is that I want to show you a connection between electron configurations and the periodic table. So this is kind of a way to check your work. So this is a way for me to kind of start to introduce like why the periodic table is shaped the way it is. It turns out that it's everything to do with the number of electrons that can fit in the different sublevels. So for example, the S block are these 2 layers right here, or columns. All right, well, S's hold 2 electrons, so 1, 2. Okay, so that kind of matches. The P sublevel has 3 orbitals, which is 6 electrons. So the P block is this area on the periodic table that is 1, 2, 3, 4, 5, 6 columns across for the 6 different electrons that could fit in the P block. The D block, so probably without even counting, you could predict how many columns is this across. The D has 5 orbitals, 10 electrons, so you're right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then the F block, again, without even counting, you could figure it out. Oh, 7 orbitals, 14 rows, and it is. The F block is 14 across. So here's how you use it to check your work. Silicon was right here in that previous example we just did, and the last part of silicon ended in 3p2. So P2, meaning the silicon should be in the P block, the second column over. P block, 1, 2, second column over. So it's a way to kind of double check your work. There's a reason that the silicon is located right here and its electron configure ends in 3p2. And then cesium was the other example, and cesium was right here. If you remember in our example, or look back in your notes, it ended in 6s1, meaning that it's in the S block, first column. So yep, S block, first column. So there's a connection between the periodic table and the electron configuration. Neither of those things are random. All right, why don't you go ahead and do a level 2 question, a great level 2 question. If you want an example, pick any element on the periodic table and say, write its electron configuration. And then you could use that Aufbau diagram pattern to map out or address out the electron configuration. Or you could come up with your own level 2 question. Go ahead and pause, finish that level 2 question. All right, welcome back. So the last piece of this note's just a little bit left. I just want to talk about the different quantum numbers that are needed to completely describe the electron's position or its address. Now, technically, we're only focusing on 2 of them. We're focusing on the principal quantum number, which is the energy level. So N is the symbol 1, 2, 3, 4, 5, 6, 7. And then this angular momentum, which is technically the sublevel, which we call SPD and F. In the Schrodinger equation, they would have to have numbers related to them so that you could plug them into the math equation to get that graph that shows the pattern of the electron cloud. But we've just focused on the sub energy level and the sublevel. So N and then the sublevel as SPD and F. Now, technically, there are also the orientation in space. So which axis is it on? So is it on the X, Y, or Z axis? That's the magnum quantum number. And then also the spin. Because remember we said that it could be spinning this direction or this direction when they share an orbital. So that's like a plus or minus is kind of that idea. So technically, if you wanted to fully describe an electron's position, it would not just be its energy level and sublevel. It would be the energy level, the sublevel, what axis in space is it on, and which direction it is spinning. To move forward, you're only going to use the quantum numbers 1 and 2, but if you wanted to know the rest of the story, we do talk about the others in AP Chem. So if you haven't signed up for AP Chem yet, and there's still time, you could do it. And if you're like, oh my gosh, I want to know the rest about this story, there would be your reason to do so. Okay. To finish this off, so the plan for the rest of this time, I have a reading for you posted on Schoology that talks about a couple elements that are exceptions to that electron configuration pattern. Find it on Schoology, put it in your Notability Unit 7 folder, and then read it before you do the assignment, because now I want you to practice some things about electron configurations, but you need to know those couple exceptions because they could show up on that assignment. So the worksheet is due tomorrow. Make sure you read the reading first. And then you can mark up the text and, do the normal things you would when you're reading something. But then that goes into your Notability. Okay, so that caps off our information for today. Go ahead and do a level 3 COSTA question. You'll do a summary at some point. Don't forget to go back and do those things to finish off our topic on electron configuration. And that's it. That's the end of part 4, or day 4, part 2. So here's the things to work on. Everything from day 1, 2, 3, and 4 part 1 should all be done. So if they're not, make sure you go back and finish those things. Put the exceptional electron configuration reading into Notability. Do the reading, don't forget about that. Complete the electron configuration sheet. That's an assignment on Schoology. There are some practice problems you can do. Remember, practice problems, they are posted on Schoology. You put them in the back section of your notebook. If there's A, B, C, D, remember you only have to choose one of them. You check your answers. It's a way to make sure this makes sense beyond the few things that I'm asking you to do as real assignments. Remember, if you have questions on any of this stuff, I do have office hours every school day from 1 to 2, where for sure you'll be able to get a hold of me. I have them other times too, but remember, it's every day. Every teacher has office hours from 1 to 2. I will see you at our next Zoom meeting. If you're in hours 1 or 3, that will be on Thursday. If you're in hours 2 and 4, our next Zoom meeting will be on Friday. Thank you so much for logging in, and we will see you next time.